good morning to all of you. My name is Akash Gautam. Currently, I work as a consultant at Kubernetes. So, my roles and responsibility is basically to help our customers adopt cloud native using our products as well as others tools and technologies which are part of the cloud native ecosystem, right? So, in this session, we will talk about application delivery on Kubernetes, right? So, the applications that we deploy on Kubernetes, they needs to be exposed outside the Kubernetes network or the private network on which the Kubernetes cluster lives, so that the intended users of the application can access it, right? These users can be human users who are trying to access the application using a web browser, but at the same time they can be some other application also, right? Other application that needs access to something which we are hosting on our Kubernetes cluster, right? So this is the agenda. So we will start with services. We will look into how services can be used to expose Kubernetes applications. Then we will discuss about L7 proxies, self-managed L7 proxies, right? And then we will move to ingress. So most of you must be already familiar with ingress, that ingress is how we expose our application. But the thing is, when Kubernetes came into picture, ingresses were not there, right? They were introduced few years later. So I just wanted to touch upon what our options were before ingress came into picture, right? Then we will discuss some of the limitations of ingress. And then we will look at the latest project in this space, which is the Gateway API project. We will discuss how Gateway API project addresses the limitation of ingress and what other benefit it brings to the table. Okay. So whenever we create an application on Kubernetes, we often create a service also with it, right? So services basically provides us with a stable network endpoint, which various clients can use to access our application, because our applications are running on pod and pods can come and go. So services helps in providing a stable endpoint which clients are always know that it won't change, right? And services can be of various types. So by default, the service that we get is a type of cluster IP, but this service exposes application only within the Kubernetes network. But our intention here is to expose it on the public internet outside our private networks. So this doesn't fit the bill, right? Other type of service we can use to expose our application is a service of type node port. As the name suggests, this service exposes the application on the nodes, on each of the worker node on a certain high range port, right? So these port range are by default 30,000 to 32,000 something, and it gets exposed on each of the worker node. So the limitation of this approach is quite obvious. First of all, our application is getting exposed on non-standard port, right? So these ports are not standard ports like an HTTP port or an HTTPS port. So the clients who needs access to our application, they need to know on which port our application is running, right? And if we have 10, 15 application, then for each application they need to know the port, and for some reason if that port change, then that information also needs to be with them somehow. And another major limitation of this approach is for our application to be reachable from the internet, the node IPs that we have, they also need to be publicly available, and which is a big security threat and something which is never recommended, right? So due to these two major limitations, the service of type node port is also rarely used, never used actually for production grade application. Maybe if we want, we can use it some for development purposes, or maybe something that is we just need to expose in our private network, but never for something that needs to be accessed from the internet, right? So this is the limitation that we just discussed. So another type of service which we can use for exposing our application is a service of type load balancer. So this is much better compared to the previous approach. So in this case, for each of our application, a load balancer gets created in our environment. If the infrastructure provider which we are using, if the infrastructure providers has a load balancer service, then one load balancer will get created for each of our application, right? And if we are on a platform that doesn't have a load balancing service, then even that is something we will have to manage on our own using something like a Metal LB, for example, right? And these load balancers are created usually on the public subnet so that the end clients can reach them. And they are not only just created, they are also configured by Kubernetes itself. So if my node changes, for example, my cluster scales up and I have a new node, then that configuration is also updated on the load balancer, right? So the entire thing is managed from within the Kubernetes. Yeah. But yeah, so this service also has a few limitations. First of all, is very high cost. So if I have like 15 applications, then I will have 15 load balancer cater for the exposing them, right? And which can be very, which can lead to very high cost, especially on top tier cloud providers. And along with that, we will also have to manage all those load balancer, right? So for each load balancer, we might have to create new DNS entries. We might have to create firewall rules. So other operational overheads are also associated with managing a large number of applications. While managing large number of applications using service of type load balancer, right? Another major limitation, and this is not just limited to service of type load balancer, but Kubernetes services in general. Like so Kubernetes services operate on the layer 4 of the OSI model, right, which is the transportation layer. So as long as our requirement is limited to that, our client will make request to our load balancer on a certain port, and that load balancer will forward the traffic to our application on a certain port and move the traffic back and forth between the client and our application. We can consider using services, but actually the routing requirements are never limited to just port to port routing, right? We might want to do routing based on the path specified by our client in the request. We might want to do routing based on the header specified by client in the request, or based on the host name that they are specifying, right? So for all those things to work, we basically need something which works on the application layer of the OSI model, or commonly referred to as L7, right? So instead of using a service of type load balancer, what we can do, we can deploy an L7 proxy of our choice, right? So there are many vendors who provide L7 proxies. We can use Nginx or any other which we want, right? So we can deploy this L7 proxy on a public network, expose our application on node port, and allow the L7 proxy to access our application using the internal IP of our nodes, right? So with this, we don't need to manage a ton of load balancer. This approach is slightly better scalable. So even if it scale up, we can just keep configuring our L7 proxy to forward traffic to the newer app that we deploy, right? Yeah. But there are a few limitations of this approach also. First of all is like operational overhead. So actually managing this L7 proxy can be very cumbersome and scale, right? So for each application, so as long as we have one or two or few 4 or 5 applications, it is still manageable. But when we need to do it at scale, right? When we have large number of application, then managing the configuration of this and these L7 proxies becomes very cumbersome. Another thing is that now that we are hosting these proxies ourselves, so along with the Kubernetes cluster, like so managing a Kubernetes cluster itself requires lots of administration, right? Along with that, we will also have to manage the infrastructure on which we are hosting the L7 proxy, right? So and also these L7 proxies are communicating with our apps using the internal node IP, right? So and we know that in the Kubernetes environment, these nodes can also come and go, right? The nodes can scale up, scale down. So every time that happens, what we will have to do is we will have to update the upstream of these L7 proxies. We will have to restart the proxies, right? So this is also very difficult to manage in a highly elastic environment. And yeah, so these are the limitation of this approach that we just discussed, right? When we are managing an L7 proxy ourselves. So to address these challenges, Kubernetes introduced ingress and ingress controllers, right? So what ingress basically is? Ingress is a native Kubernetes object or an API, right? What it allows us to do? It allows us to define our routing requirements, like how we want to route traffic to our applications that we have deployed. And the schema that it gives us is much simpler as compared to the native configuration of various L7 proxies, right? So it's a simple YAML, as we can see. And now we can just, as this is inside the Kubernetes, we can directly specify the name of our service. We can even use secrets to specify the certificates for TLS routing and all other features we can get, right? And then, so we know in Kubernetes everything work on an object controller or an object operator pattern, right? So whenever we create an object, we also need a controller or an operator that continuously reconcile the object, right? And reconciling an object can mean different things for different object, right? For example, reconciling an deployment means running the desired number of replica of the image we specify in the deployment. Similarly, reconciling a PV means creating the storage of the desired size and configuration, right? So similarly, reconciliation in case of an ingress controller means reading the ingress that we have defined, right, and then convert it into the proxy specific configuration. So the complexity that we had regarding configuring the L7 proxies ourselves, that complexity is completely abstracted from the user or the cluster admins, right, who needs to configure the routing. And also this control loop, this controller continuously watches any changes to the ingress object, and whenever it changes, it applies the corresponding changes to the L7 proxy also. So this way, the challenge that we had regarding continuously refreshing our configuration and restarting our proxy server, that challenge is also taken care of, right? So the ingress controller is essentially the proxy that we are discussing, like it's an L7 proxy, but along with that, it has a additional responsibility to continuously reconcile the ingress object that we have in our clusters, right? And L7 proxies have been around for quite some time now, like organizations were already using it even before Kubernetes came into picture, right? So it was never expected that only services will meet all the routing requirements that different organizations have, right? Yeah, but there is still one problem, and that's the problem with which we started, right? Because now what happens is, now my L7 proxy is running inside the Kubernetes cluster itself, right? And we were discussing how we expose it over the internet, right? And now we need to expose our ingress controller, and for this we can now fall back to the services. So we can create a service of type load balancer and expose our ingress controller. But now, as compared to earlier, we just need to expose one application. So all the overheads that we had with service of type load balancer, those overheads do not apply anymore, right? And this is how you will see most of the organization using ingress today. Like they will deploy the ingress of their choice, ingress controller of their choice. They will create a load balancer to front it, and then client can make request to the load balancer, which forwards the traffic to the ingress controller, and then ingress controller refers to the ingress to map traffic to different services that we have deployed, right? Yeah. So, and another thing to note here is that the challenge for Kubernetes was not to solve the routing problem, right? It was already a solved problem. The main challenge was how to integrate these various L7 proxies provided by different vendor into Kubernetes, right? How to make it Kubernetes native, right? How to simplify deploying an ingress or an L7 proxy, how to simplify the operation, how to simplify the upgrade. Because the more things Kubernetes can support out of the box, the more feature rich it becomes, and the more appealing it becomes to different organizations for considering moving to Kubernetes, right? Yeah. Yeah. So ingress have served us really well, and they continue to do so as we speak, right? The APIs are fairly stable. There are a number of vendors who provide ingress controller implementation we can choose from, and then in general they meet many of our requirements, right? But yeah, we know how rapidly Kubernetes is getting adopted in the software industry, right? And because of this rapid adoption, a wide range of applications are getting deployed on Kubernetes, and these wide range of applications are managed by a diverse set of teams, right? So teams of different organization structure and different sizes are managing applications and sharing the underlying infrastructure. And because of this, some of the limitations of ingress started emerging, right? One of the first limitation is limited protocol support, right? So with ingress, we are able to do only HTTP and HTTPS based routing, but yeah, it is unlikely that only these two protocols will satisfy all our routing needs, right? Another major limitation is lack of native support for advanced routing. So with ingress, we can do path based routing, we can do host based routing natively, but other routing requirements like HTTP header based routing or doing a query parameter based routing, rewriting some response header. So all those things, for all those things, we rely on annotations. The problem with annotation is like they do not come from the specification, they come from the metadata, right? and what happens is that because of that they are not actually part of the core API. So in that case, even though ingress was intended to be vendor neutral specification, if you look today, whenever any advanced routing requirements comes up and you compare the ingress configuration of different vendors, they start becoming vendor specific, right? Because these annotations are entirely up to the vendor, what annotation they want to specify and how they want to implement it. It is entirely up to the vendor, which doesn't ensure standardization across vendors, and also it doesn't ensure conformance, right? Yeah, another limitation is the operational constraint, right? As we discussed that ingress, like other ingresses or the network infra that we have in the cluster, they are meant to be shared between teams, right? So different teams share the infrastructure, and whenever some sharing happens, it is desired to have a clear separation of concern, right? Who is responsible for what, so that different teams can work together at the same time, do not disrupt the work of each other, right? So these operational constraint also, so ingress has mechanism to control this, but it is not as well defined or as fine grained as it should be, right? So all these limitation actually encourage the SIG network group of Kubernetes to work on something called the gateway API. So gateway APIs, they are a collection of APIs, they are collection of custom resources, CRs or CRDs as we call it, right? And they model the service networking in Kubernetes just like ingress, right? And they are deployed as CRD. So this is also a difference as compared to ingress, right? Ingress are a native Kubernetes object, but these gateway APIs, they are deployed as CRDs, right? And because of this also we get some more benefit out of it, as we will discuss very soon, right? Yeah, so the key APIs in the gateways are gateway class, gateway and routes. So we can start with gateway class. So gateway class is a template for the types of gateway, right? It just groups related gateways together. It specifies what kind of network infra you have in your cluster, and this gateway class are created by the vendor. So whichever vendor you choose to provide you with the gateway API implementation, that vendor will be responsible for creating the gateway class. So if you have multiple vendors, you will have different gateway class, and accordingly you can use any one of them at a time, right? Yeah, so just specify which vendor will ultimately do all the heavy lifting of routing the traffic, right? So this is how ingress class look like. It is a very simple specification, right? As we can see, we are just specifying the controller name. So this is coming from Cilium, so we have the controller specified accordingly. If it was from some other vendor, then the controller name will change, right? It is similar to ingress class that we have in ingress, and also it's similar to our storage class also. Like in storage class also we specify the provisioner that we want to use. The other object that we have is a gateway, right? So gateway is the object based on which the underlying proxy configures itself, right? So in the gateway we specify on which port our proxy intends to accept traffic, on which protocol it intends to accept traffic, which routes it wants to allow or deny, how it wants to handle TLS. So all those administration related to the proxy itself, they are defined in the gateway. And yeah, so this is the structure of a simple gateway. So here we specify the gateway class name, which is specify which gateway class it is coming from, and then we specify listeners, basically on which port we intend to accept traffic, and then the protocol, right? And then we have something called routes, and so these routes are protocol specific. So they specify rules based on which once the traffic reaches the gateway, how that traffic gets translated to different services deployed on Kubernetes or different apps deployed on Kubernetes, right? So these specify that mapping, like once the traffic reaches the gateway, then what operation it needs to do and how the request coming from the clients gets mapped to the our application, right? So this is how a gateway route configuration look like. So you can see the kind is HTTP route. So for each protocol we have a separate CRD or a separate API, right? We will discuss what benefit this brings to a table. So this is how configuration look like. You can see that we have a native support. So in the specification itself, we are able to do header routing or query parameters, Everything is supported out of the box, right? Yeah, so this is how this various APIs fall into place, and how this is how they map different or different roles we might have in an organization, right? So first of all, we get the gateway class. It comes from the infra provider, which is our choice of gateway API provider. It can be Nginx or Cilium or Kong, whichever, right? Then we have the operator. So cluster admin or cluster operator, they are responsible for creating the gateway. Everything related to the gateway is controlled by them, and then the application developer or the testing team, they have complete liberty to specify the routes that they want, right? Because if they are developing application, they should have the liberty to specify the routing. Similarly, if the team is deploying an instance of an application for doing for testing purposes, they can also define the route, or maybe they just have a separate host name for traffic. So all those liberties with the team, right? And here we can see there is one like difference as compared to ingress. So in ingress we have a single API where all the where many of the proxy related information as well as the route, they both live in the same ingress object, right? But here that object has been split into two. The rules, the concerns which are of developers or different team, in most of the cases those concerns have been separated out, and all the configuration related to the proxy itself, right? So if I am a cluster admin, I won't want different teams to make any change to the proxy or ingress controller or gateway controller that I have configured, right? I won't want developer or QA team to make any changes to that. So in that way, the ingress has been split into two, right? So all the things that are related to the proxy itself, they have been taken into gateway API, gateway object, and all the things related to routing, they have been put into separate object. And not only that, those routes are also protocol specific. So what this allows us to do, now we have different route for each protocol. So we can be more expressive, right? We can have some common field, and then we can have things which are specific to the route itself. So this allows us with more configuration option as compared to ingress, right? Yeah, so these are the benefit of gateway APIs as we discussed. So it is much more expressive, it is much more portable, because now most of the things are being supported out of the box. Everything is coming from a specification. So any valid vendor who wants to be a valid gateway API provider, they need to implement all the specifications, right? So we are no longer relying on annotation for any of the features. Role oriented, yeah, as we discussed, this is the APIs try to model the organization role. So they are much more they represent the organization structure in a slightly better way as compared to ingress. And not only that, there are other capabilities also, right? So whenever developer defines a route, like if we go back to the route, yeah, so in here we can see that when we create a route, we specify the gateway, right? So so while creating the route, we specify the gateway. Similarly, gateway can also specify which routes they want to serve. So there is a two-way handshake basically between the route owner and the ingress owner. For example, if I go back to, yeah, so in gateway I specify what kind of we can specify what kind of routes we want to allow, right? So and from which namespace we want to allow. So here the namespace set is same. So only the routes which are in this namespace will be served by this gateway, right? Similarly, we can specify selectors. We can specify labels based on which we want to filter the routes. So only the routes which have those labels, they will be served by this. Only the namespaces which have the label that we specify, they will be served by this gateway. And even in the namespace itself, we have option to allow or deny certain routes, right? So all this flexibility just allows different team to better coordinate, right? And when we combine these capabilities with RBAC, we get a much more well-defined way of managing and access and sharing the underlying infrastructure, right? Yeah. And not only that, there is more granularity also. So if I have a gateway which has multiple listeners, my route can even be as specific as, like, I want to attach only to this listener, to only a specific listeners of this gateway, not all the listeners, right? So all those granularity is also possible. Yeah. So so gateway API has provided out of the feature for many of the features, for many of the routing requirements is now being supported out of the box, but still they are providing some extension points, right? Because it is definitely still the gateway API cannot meet all the routing requirements which might emerge in future, right? So for that they have provided with some backend extensible point. So so one of the extensible point we have is the backend ref. So this basically allows us to route traffic to non Kubernetes services, right? So by default all traffic is routed to the Kubernetes services, but in some cases we might want to route traffic to some other entity, right? For example, an S3 bucket. So I have a static, I am sharing an ebook, for example, right? And I want, whenever my user want to download, they click a link. I don't want to run a web server for it. I just want that traffic to come to my S3 bucket and allow the user to download the file, right? So for that we can customize the backend ref also. There is HTTP route filter using which we can configure hooks to different phases of the request response and then do some operation over there. So with this and then there are custom routes. So as these routes are protocol specific, right? So if I want to support a new protocol, I can introduce a new custom resource or a new API and then implement it in my controller, right? So and for example, right now even gRPC protocol is under experimental feature for gateway APIs. So all those benefits are also there. So and these endpoint and this extensible endpoints, so what they allow us to do is they allow us to extend gateway in a API specific manner, not with the help of annotation, right? Because these all will be separate APIs, new APIs, and the team is also encouraging people to share their use cases, and if they find something common, then they will define conformance and standard around that as well. So this way it can be extended as well, right? One of the common thing is people think is what happens to ingress. Is gateway API intended to deprecate ingress completely? So ingress are, as I said, is very stable. These APIs are still in progress, like under rapid development. So ingress are much more stable. They are battle hardened. We have been using them for a long time. This is definitely a superset of ingress, but that doesn't mean that ingress is going away anytime soon. Right?
So does this gateway provide some multi-cluster feature as well, like ingress provide MCIs?
So right now the routes are being shared across the namespace, but in future as the MCS APIs get mature and other multi-cluster use cases come up, it is fairly possible that we extend these gateway APIs to allow routes from different cluster itself. Right now routes are shared across namespace boundaries. Okay. So in future it is possible it gets extended across cluster boundaries. So you have gateway in one cluster, you allow attaching routes from other cluster. Definitely possible.
Thank you.